Hi, welcome back everyone. This is the third video on gravitational field and which is the last. In this video I'm going to talk about satellite motion and escape velocity. And before coming to the satellite motion, I would like to discuss a circular motion of an object around a planet. For example, you can consider a moon is orbiting around the earth. And as we know from our knowledge of classical mechanics, object should have a centripetal force in order to move in a circular path. Here in this example you can see a stone is attached to a string and it's moving in a circular path. So here the required centripetal force is provided by the tension acting on the stone by the string. So similarly, if you take a circular motion of a planet orbiting around another planet, the required centripetal force is provided by the gravitational force. So here I am going to consider a mass of simple m moving in a circular path around a planet of mass capital M. Here I consider the velocity of the object is v and the radius of the orbit is simple r. And now I consider the object and apply Newton's second law, which is F equals ma. So I can write using F equals ma. So F is equal mv squared over r for centripetal acceleration, and here the required centripetal force is gravitational force acting on this mass from this mass. So I can write that force is equal g m over r squared. Okay, so I get from this if you subject v, we can get expression for the velocity that is given by square root of gm over r, which is independent of its own mass. So this speed is independent of the mass, whether it's 1 kilogram or 2 kilogram or whatever. Okay, and we know v is equal r omega, where omega is the angular velocity. So from that we can obtain expression for omega that's given by square root of gm over r cube. And the next thing, periodic time, that means how long it will take to come to the complete one cycle. For that we get periodic time, which is t is equal to 5 omega. So for omega, if you substitute this, we get a expression for periodic time. So it's given by this equation, and if I square both sides, I get this equation. Okay, so here this is a constant, and gravitation universal gravitation constant, which is obviously a constant, and the mass of this planet is a constant. So I can write t squared is proportional to r cube. This is Kepler's third law, which says the square of the period time of a planet is proportional to cube of a or radius of the orbit. Okay, so let's move to satellite motion. First we should know there are artificial satellites and natural satellites. For instance, moon is a natural satellite, and an artificial satellite is an object which is placed intentionally in orbit. And the world's first satellite is Sputnik 1, launched in 1957 by Soviet nation, and its size is like a beach ball in diameter 58 centimeters. And currently there are more than 2000 satellites orbiting around the earth, including Skylab and ISS, which is International Space Station. And can you imagine that there are more than 2000 satellites orbiting around the earth? Anyway, let's move to the subject. So here I'm going to consider a satellite is orbiting around the earth. So in this picture I'm going to replace a satellite here, and this is my lovely earth, and here still I consider the mass of the satellite is simple m, and starting from F equals ma to the satellite and do the max, we get the following same results. So we have our satellite moving in a circular orbit around the earth, and the next thing we will obtain expression for its kinetic energy and potential energy. In the previous video I discussed the potential energy of a mass and distance simple r from a center of planet is given by this equation. Therefore this gives the potential energy of this satellite, and we know the kinetic energy is given by half mv squared, and we already derived an equation for v, which is velocity, that's given by this. So substituting that in this equation, so it yields, we get this kinetic energy is gmm over 2r, and the total energy is given by the addition of kinetic energy and potential energy. So we get the total energy is equal to minus gmm over 2r. And here we can note several things, that potential energy is twice the kinetic energy but it's negative, and here the value of total energy and kinetic energy equal but opposite in sign, here plus gmm over 2r and this is minus gm over 2r. And the next thing we will see how this potential energy, kinetic energy and the total energy of a satellite varies with distance. Okay, so it's given by this figure. So here you are always free to pause the video and look for a longer time. And the next thing, let's consider that you want to launch a satellite to an orbit from Earth's surface. For that you need to project the satellite with some speed. That means you have to give some kinetic energy. And let's see how can we calculate that. Here first let's consider that you want to project the satellite at a speed such that when the satellite reaches to an orbit, its speeds become 0. For this process you have to give certain amount of kinetic energy, and that energy, that's what mean by minimum energy required. And to calculate that we can use energy conservation principle. So the total energy at the Earth's surface is equal to total energy at the orbit. And here this term is the kinetic energy of the satellite when it's at the Earth's surface, which is we want to find out energy required. And this potential energy of the satellite when it's at the Earth's surface. And here the kinetic energy of the satellite at the orbit is 0 because we set to be 0 in order to get the minimum energy required. And this is the potential energy of the satellite when it's at the orbit. And we know the potential energy of the satellite when it's at the Earth's surface is given by minus gmm over capital R, where this capital R is the radius of the Earth. And at the orbit we can write that potential energy is given by minus gmm over R. So simplifying this equation, then we will get the minimum energy required, that's given by this expression. Okay, and then next thing is total energy required. Here you have to give energy to the satellite, not only to send the satellite to the orbit but also get this speed. So here you have to give an additional kinetic energy to the satellite. So here also you can find the total energy required using energy conservation principle. So total energy at the Earth's surface is equal to total energy at the orbit. So apart from this equation, the only additional term is this kinetic energy term, which is gmm over 2r. And if you subject energy required in this expression, then you will end up with this expression for the total energy required. And the next topic is geostationary satellite. Well, geostationary satellite is a satellite which remains stationary relative to a point on the Earth. For example, let's say you are here on the Earth and you are looking vertically upwards and you can see a satellite, okay? And let's say after 3 hours or 4 hours, okay, we know Earth rotates, so you are not here, so somewhere here. So, and now you are looking vertically upwards, still you can see the satellite because it remains stationary relative to point, so it rotates along with the Earth. So actually geostationary satellite has same angular speed as the Earth, so same periodic time as the Earth. So if we take the angular velocity of the Earth as omega, then the angular velocity of the geostationary satellite also omega, because both has same angular velocity. And we know the periodic time and the angular velocity is related with this equation, so we can get omega is equal to 5 over t. So if you want to find the angular velocity of a geostationary satellite, then what you have to do is you can substitute the time 1 day, because we know the periodic time, that means Earth takes 1 day to rotate itself. So here we have to substitute the time in seconds, so 20.60 into 60 seconds. So you can get the angular velocity of the geostationary satellite. Okay, and so this is about geostationary satellites. And the next topic is escape velocity, which is actually the last topic from gravitational field chapter. Okay, so let's see what escape velocity is. Well, the escape velocity is defined as the minimum velocity required for an object to exit Earth's gravitational field. And theoretically we know Earth's gravitational field spread throughout to infinity. That means the minimum velocity required for an object to move to infinity. Okay, so by considering energy conservation principle, I can write the total energy of this object at the Earth's surface is equal to total energy of that object at infinity. So we know the total energy is kinetic energy plus potential energy, and at the infinity we know the potential energy is 0. Also the kinetic energy is 0 because we want to get the minimum velocity. So that's the escape velocity by definition. So we get escape velocities from subjecting VE, we get square root 2gm over r, and we know since gm is equal to gr squared, we also get escape velocity is equal square root of 2gr, and here r is the radius of the earth, here simple g is gravitational acceleration, and from this equation we know capital G is 6.67 times 10 to the power minus 11 Newton meter squared per kilogram squared, and the radius of the earth is 6,400 kilometer roughly, and if you know the mass of the earth you can find out the escape velocity of the earth, and if you do the max you will get it's about 10.5 kilometer per second. That means if you throw this with the speed of 10.5 kilometers per second, that means this has to go 10.5 kilometers in 1 second. Okay, if you throw this with such a high speed, this won't come back, because we know if I put this up, this again falls down because of the earth gravitation. So if you throw this with this much of speed, what happens is it won't come back. So that's what escape velocity means. So for example, now I say we know the escape velocity of object is 10.5 kilometers per second and it's independent of the mass. So whatever, if you take 5 kilogram or 10,000 kilogram, still the escape velocity is same. And if you throw this with 10.5 kilometers per second with that speed, we know it won't come back. So if I throw this with speed of like 15 kilometers per second, still this won't come back. So that is about escape velocity. And I think from here the entire gravitational field chapter is finished. And if you have any questions or anything, you can mention in the comment section below. I believe these videos benefit you all, and I hope I could meet you once again in another video. Until then, take care.